All right, welcome back, Math 30-2s. We're on our second lesson in Unit E, applications of exponents and logs, and we're going to specifically talk about finance, okay? So investing money, if you deposit money in a financial institution like a bank, you are in effect lending money to them. In exchange, the bank pays you interest, like opposite of, loans and credit cards. And there's two types. There's simple interest and compound interest. Simple interest is just a linear equation, much like you would have seen in Math 10C. And then compound interest, that's where things get interesting, and that is our exponential type, and the reason why we're talking about it in this unit. So if we just look at simple interest, usually just for short-term investments of 1 year or less, or long-term investments where the annual interest is paid to the investor and not reinvested, like it's not put back in to build. So if you invest $500, earning at a rate of 6% per year, how much interest would you earn in 1 year, half a year, 1 month? Okay, so then you would just have $500. Okay, and then for 1 year, that's 6% per year. So then that's going to be adding on. So one way of looking at it, you could do like 1.06, because that's what you're adding on. That would give you your total. If you just want the amount of interest, which I think, yeah, this is what it's asking, how much interest. So we would just do the 6%. Ooh, and I almost forgot a zero there. And so 500 times 0.06, so $30. So you would earn $30 in a year. Half a year would be $15, and in 1 month, that'd be 30 divided by 12. So 30 divided by 12, a whole $2.50. Okay, not exactly raking it in. If R is the annual interest rate expressed as a decimal, and P is the initial investment, calculate how much interest would be earned in, okay, so we're basically doing the same thing, except for now we're putting in the numbers there. Okay, so the amount of interest, okay, is going to be equal to that original amount. Okay, and then the rate of interest is expressed as a decimal, so that's going to be the, so just R, okay, and then in 1 year, so that's going to be multiplied by 1, okay, and then for half a year, it's going to be PR, and then 1/2, and I is equal to PR, and then, okay, just T years, then I would just put T. And so that's where this formula comes from, where I is the amount of interest, P is the principal, so the initial investment, R is the annual rate of interest expressed as a decimal, and then T is in time. Okay, and that gives you the interest itself, which then if you wanted to know how much money you had total, you would add to the original amount. Okay, so class example 1, Millie invests, so we've got, that's our principal. There's our rate, and then our 6 months, so that's going to be half a year, right? Because T is in years. Calculate after 6 months. So then the simple interest, okay, so always put down your formula first. Okay, 2,350, okay, 0.07, and then half, okay? And then you just have to substitute that all in. Oopsies, so 2350 times 0.07 times 0.5 gives us $82.25. $82.25. Okay, and then the overall value of the investment. So the value is going to be I plus P. Okay, so the 82.25 plus the original 2350. Okay, so plus 2350 gives us $2,432.25. So $2,432.25. Okay, so that's a nice linear relationship right there. So now we're going to talk about compound interest. So in simple interest, the principal at the beginning of the second year is the same as the original. Okay, Yeah, the principal at the beginning of the second year is the same as the first year. In compound, that interest earned during the first year is added. So interest earned during the first year is added to the original principal to form a new principal. Okay, this is how you would make money faster, more of it faster. Okay, so then we're going to do a little bit of an investigation on the next 3 pages to help us just kind of understand the difference between the two. Okay, so if a bank offers 2 types of savings bonds, so the regular savings bond, which is simple interest, so that's going to be our I is equal to PRT. Okay, and then the compound savings bond, which pays at 9% per year, compounded annual, and the initial investment is going to be $15,000 each. Okay, so for the first one here, 9% of 15,000, so 0.09 times 15,000. $13.50. Okay, so that's not too bad. $1,350. So then you can see here at the end of year 1, we've added, so this is the 15,000 plus the 1350. So that's what it's going to be each time. We are adding 1350 to our amount. Okay, so then let's just finish this table. So 21,750 plus 1350 is 23,100 plus 1350, 24,450, and plus 1350, 25,800. Okay, so we completed the table. So we see that after 8 years, we are at 25,000. So we've gained $10,800, which isn't too bad. Okay, let's look at compound interest. So this is how we start breaking it down. Okay, and then I just want to let you know we are eventually going to be looking at the formula here. I like to see the formula first before. If you don't, then sorry about the spoiler. Okay, so that's what we're aiming towards. So remember, the interest is reinvested each year. So if we have our first year here, we've got the principal, we've got the interest, okay? And so the interest we know is just multiplying it by that 0.09, which is what we did there, okay? But now when we write it like this, we can factor out that 1,500 right there, okay? So 15,000 divided by 15,000 is 1, and 15,000 times 0.09 divided by 15,000 is 0.09. And then we can simply just add those two together, okay? So then at the end of the first year, that is our value, okay? Which was the number that we added to get the 16,350. Okay, so now at the end of year 2, okay, we've got this. This is now our principal, okay? And so that's our principal. That's the amount of interest. And so now this is the new interest that we've got right there. Okay, so once again, we're gonna factor out 15,000, but we're gonna factor out 15,000 times the 1.09, okay? Because those are two values. It's like saying if we had like AB plus ABC, and then we write it as AB, and then that's 1 plus C, okay? So that's the same pattern right there. So then they basically just simplify it down, and we see at the end of year 2, this simplifies down and we've got a power of 2 there at the end of year 2. So we could say, okay, well, like it's like there was a 1 there at the end of year 1. So let's go to year 3. So same idea. This amount now is going to be our principal, and then we're going to multiply it by the 9% to get our new value. Okay, so we did that, and then we factored out now the square of the 109 because it was in both of those right there, okay? And so then we can write 15,000, and then this is gonna be 1.09 as well. So I'll just write it out all, but we probably could, oopsies, there we go, done it in one step. And then I can combine this, right? This is 1.09 to the 3. So essentially what I had here was I had x squared times x, which then simplifies into x to the 3, right? That's just exponent laws kind of thing. All right, so let's go to the top of page 277. So we've got this work. And so we obviously now have that pattern that at the end of each subsequent year, we're going to have this this expression, and then each time we're going to add our power is going to increase by 1, or our exponent. Okay, so then we just need to do this 6, slightly repetitive, but just so that we can see the pattern, because we're deriving an equation from this. Okay, and so then the last one, that's just going to be n. So however many at the end of whichever year, okay, it's going to be written to the power of n. So this would just be the same. 1.09 n. Okay, and so I'm going to crunch these numbers. Okay, so I crunched the numbers there, and there they are. You should put them in your calculator, make sure that you get the right numbers. I used the shortcut where I just copied and pasted and then like put in a different number there so that it was a little bit easier for me. But yeah, so those are the data points. So at the end of each year, this is the amount that we made. So just to compare right here next to the simple interest, so I made about $4,000 more by the compound interest versus the simple interest. Okay, and so there is our overall formula. Okay, so now they want us to plot the data from the simple interest here. It says don't join the points. And so we're gonna take all of these, okay, or sorry, all of these. So 1, 2, 3, 4, 5, 6, 7, 8. So there's our years. And we're gonna plot them here, okay? So the first one here, like at 0 here, okay, we started at 15,000, right? So I'm gonna plot these on here. You should take the time to plot as well. Okay, so there's the points right there. I did my best to plot them. They actually kind of think, I'm gonna look at 4 again. 4 is 21, 170, so 21, which is close to, yeah, that's pretty good. I just felt like it should kind of curve a little bit more, but that's okay. This one probably at 29.88, it's probably actually a little bit higher. Okay. So the graph shows the simple interest bond is growing in sorry, I didn't do the simple interest. Let's do the simple interest ones here. We have to do these ones here. I'm gonna go get a different color pen to do them right here. Okay, so there in my blue, that's my simple interest done right there. So simple interest, compound interest. Graph shows that the simple interest is growing linear, so that's just a straight line. If we grab a ruler, move that out of the way. If we grab a ruler, we see that it fits really nicely right there, whereas the ruler for the orange doesn't really fit because it's an exponential form, okay? So the graph shows that, exponential. So we know that it can be written, so just like generally in this form, where n is the number of years, a is the original value, and b is what we're expanding by, okay? So state the values of a and b and write the function in this form. So a, in this case, is 15,000. B is 1.09. So then therefore A is equal to 15,000 multiplied by 1.09 and then to the power of n, okay? And how do the values of A and B relate in this scenario? So A is the principal and B is the interest rate plus 1. So since it's growing, it would be 1.0 whatever. If we're talking about a decay, then we would subtract whatever the interest rate was from like the 100%, but these interest rates, they're always gonna grow, okay? All right, so another graph here. So here is just at a kind of more detail here. So the difference between the exponential growth, so this is the y is equal to 1.09 n, and then this one is just the So it'd be in the form of y is equal to mx plus b. So that would be y is equal to, so mx, it was growing at 0.09 still. So 0.09, and I guess it would be n plus 1500, or sorry, 15,000. It's kind of hard to see, but once again, it's a linear relationship there. Okay, and so this one is extended to 20 years, so we can really see, like, so 25 years, if you just had that as a simple interest, you'd be at $50,000. But if you had indeed, I guess, like, if I extend that, then if you had done the compound interest, you'd be at, well, I should have done 20. Let's compare the 20. So we'd be at 85,000 versus like 42,000. Okay, so like almost double. Okay, all right, so use the compound interest graph to estimate the number of years it would take for the initial investment to get to 50,000. Okay, so this is this one here. So 50,000 is right here. So then it would take 14 years, okay? And then for 100,000, okay, so 100,000's here. And so we would trace it down here, 22 years. All right, so eventually we'll look at like how we would solve this without just looking at the graph. It's not that difficult, but for now, just the graph. Okay, consider an investment of 30,000 compounded annually at 5%. So PA means per annum, which means per years. Write an exponential function, which will represent the final amount in n years. Okay, so we've got A is equal to ABN, which is gonna be equal to, so our original amount, okay, and then multiplied by the 1.05, okay, n, okay. What about if we have this one? Okay, so 750 compounded at 3.5%. Okay, so same formula here. So A is going to be equal to 750, 1.035 to the power of n. Okay, so in general, okay, if A is the final amount, or the value of the bond, P is the principal, I is the annual interest rate. So the annual interest rate, we always add it to 1 because that represents like 100% carrying over. And then the number of years, we have that formula, okay? So which is explained up here, all right? So all of those examples were on an annual basis. We can, of course, have semi-annually, so that's twice a year, monthly, so that would be 12 times a year, daily, 365, etc. Okay, so in this section of the lesson, we will focus on the annual. Okay, and this is the formula that is going to match this. Okay, it's in the same exact form right here, right? YABX. Okay. So let's talk about borrowing money. So when an amount of money is borrowed, interest is charged for the use of the money. It's the exact same idea here, right? If the loan's paid off in one payment at the end of the loan period, then the compound interest formula can be used. If repayments are made on a regular basis during the period, the compound interest formula cannot be used, okay? So this is just if we're doing like the one big formula. Okay, I just had to move because it got a little loud out there. Okay, so Travis borrows $2,000 from his parents, so that's going to be the original amount, so like the P, from his parents, and agrees to pay off the loan in one payment. When he graduates, interest is charged at 3.5% per annum, compounded annually. Okay, so how much does he end at the end, at the end of the second year? Okay, so this is our A is equal to P1 plus I N, which is going to give me 2,000, 1.035, and then at the end of the second year, that's going to be a 2. Okay, so then we just have to plug that in. So enter 2,000 times 1.035 raised to the power of 2. So we've got $2,142.45. So if he paid off the loan in 2 years, how much interest would he have paid? Okay, well, he would have paid $142.45. So you would just have to subtract from the A minus P to get the interest. There we go. Okay, so I guess he wasn't able to pay off the loan after 2 years. And so when he eventually paid off the loan, he paid that much in interest. So write an exponential equation whose solution would give you the time period. Okay, so basically we're working backwards here. So we know that it started at 2000. So then if A is equal to P1 plus IN, and we know that A is going to be the 2,458 is equal to 2,000 multiplied by 1.05 and then N. Okay, so we know how to do this algebraically, or we know how to do it like graphically. You would just y1, y2 this, but let's actually solve this algebraically. Different ways you could do it. You could do the log of both sides. Okay, I think I would just do, so from here, 2458 divided by 2000 is equal to 1.05 n. Okay, so let's do that number. 2458. Actually, I don't need to yet, because I can just raise it to, like I can just do it as a log now. Yes, I think, yeah. So I would do, so log base of 1.035, okay, of this fraction, okay, is going to be equal to n. So I just put it into from exponential to logarithmic form, okay, and so then I would just plug that into here. So I've got log of 1.035, and then in there I'd have 2458, 2000, so there's my argument. Okay, and then so 5.99, so n is equal to 5.99. So then it would have been, the time period would have been 6 years. Okay, and then just a reminder, if you don't have the fancy calculator, you would just use the change of base formula. And so that would just look like, so your argument goes up top, so you would just use your common log, 2458, 2000, okay, and then common log of 1.035, okay, and that will equal the same number, okay? So if you've got this calculator where you can plug it in directly, obviously you would just do that. Okay, so you can work on those questions there, but we do have some more information to talk about. So now we're gonna do the not necessarily annually, okay? Everything is still the same. Okay, but now our I here, our interest, so I is going to be calculated as the annual interest rate as a decimal divided by the number of compounding periods per year. So if it's semi-annually, that's twice, quarterly 4 times, monthly, daily, you get it. Okay, N now, it's not going to represent the number of years. It's going to represent the number of compounding periods, total. Okay, so you take the number of years and then however many compounding periods you have, you're going to multiply them. So let's see what this looks like, okay? So if the interest rate is 6% per annum, state the interest rate per compounding period and the total number of compounding periods in each state, okay? So interest rate per compounding period, so I is going to be divided by the number of compounding periods, okay, which, do we have I don't think we have a number for that, or like a, so I'm just going to put periods, okay? So then interest is 6%, okay? So then 0.06 divided by the, semi-annually. I'm like, where is it? Semi-annually, okay? So then that's just going to be, so the 3%, but then the total number of compounding periods in 5 years, okay, that's going to be times 2. So there will be 10 total compounding periods. Okay, what if we get compounded monthly for 6 years? Well, monthly means that I'm going to have 0.06 divided by 12. Okay, and then my 6 years, I'm going to multiply it by the 12 months in those 6 years. So then I'm going to have 72 compounding periods. Okay, all right. So if we invest $1,000 for 5 years, annual rate of 6%, complete the table to calculate the final value of an investment. Okay, so if we've got annually, semi-annually, quarterly, monthly, the number of compounding periods per year, so once, twice, 4, 12. Okay, so then if we're dealing with 5 years, the total number of compounding periods is going to be 5, and then 10, and then 20, and then 60. So I just multiplied 5 by each one of these to get this. Okay, the interest rate per compounding period. Okay, so at 0.06%, or I guess I didn't need to write it over top of that, it'll be just that. And then this will be 0.06 divided by 2, which is going to be 0.03, and then 0.06 over 4, and then 0.06 over 12. Okay, and you can go ahead and like simplify all of those. I should have left myself a little bit more room. Okay, 6 over 4 is going to be like what, 1.5, so that's 0.015, and then divided by 12 is going to be 0.00005, right? Yes. Okay, so my formula is still going to be P1 plus I N, okay, where these are my total compounding periods. Okay, so A is going to equal, so it's the $1,000, and then 1 plus the 0.06, so 1.6, and then 5. Okay, and so you would just plug that in to get that amount, which we can do later. And then now let's do this one. Okay, A is equal to 1,000. Okay, and then now it's going to be, so it's the 0.03, so 1.03, but now we're being raised to the power of 10. Okay, and then still 1,000, oopsies, 1,000, 1.015 to the power of 20. And then our last one, I'm just gonna write it like this, 1.005 to the power of 60. Okay, and then let's plug these all in. Okay, and there's the numbers there, and that's how I plugged it in. Okay, so we do see that the more compounding periods you have, the more the interest is accrued. Okay, so something to think about if you are investing money. All right, 2 more questions here. So it says Christina invested $2,500 for 4 years. So there's my P, there's my N. It's compounded semi-annually, so that's going to be, my N's going to be times 2. Okay, and then my annual rate of interest, I would need to divide by 2. Okay, and then this gives me how much interest she actually made. Okay, and remember the interest is equal to A minus P. So let's set this up here. So 2,500, oh, sorry, actually plus 84326. Okay, and then the P is 2,500. Interest, we're not sure, but we know that it's going to be divided by 2, right, when we substitute it in. Okay, or we could end up doing that at the end as well. And then 4 years, so it's going to be 4 times 2, or 8. Okay, so then let's just quickly add this. So 2,500, oops, plus 84326, so 33. 33, 43, 26. Okay, so we write down our formula. Okay, I solved this and made like a complete mess of it and was like over here, so I decided just to redo it here. Okay, so we're gonna substitute in, and I'm gonna move things over just a little bit this side. Okay, 2,500, 1 plus I over 2 to the power of 8. Okay, so the first thing I would do is just divide both sides by the 2,500 right there. And so when you do that, you get 373 is equal to 1 plus I over 2 to the power of 8. Okay, so then I think from here, I think I would take the log of both sides. That's what I did before, and it worked out fine. It just got all crazy. Okay, and so then I have the log of like this right here, and I could put it in, but we'll just wait. Okay, and then I'm going to use my power rule, okay, to bring that over there. And then I can divide by the 8, I think is what I did before. Yeah, I'm going to divide by 8. Okay, and so I'm going to actually show this in here. So I have, so there's my 133. Okay, and so I'm going to enter that. Oopsies. Where'd it go? Actually, I'm going to do, there we go. Log, and it's just 10 of that number right there. Okay, and then outside of that, and then I'm going to bracket that just in case, divided by 8. So that gives me that number there. So I'm going to have 0.015779, and I'm just going to write down all the decimals that I can. Okay, and then that gives me log 1 plus I over 2. Okay, I was hoping that I could squish it a little bit better onto this side, which I did. Okay, so now from here, I think it'd be easiest for us to now turn this into an exponential. So there is a, like there's like the base right there is 10. So I would do 10 raised to the power of this, and like whatever, however many decimal places is in your calculator, 15779, etc., is going to be equal to 1 plus I over 2. Okay, and so then I can raise that. So let's do that. So I'm going to have 10, oopsies, raised to the power of that number there. Excellent. So see how it just saves the total number there, which is going to give me that number. 1.037 is equal to 1 plus I over 2. So then I'm going to subtract the 1. Sorry, I should hide my camera here. Subtract the 1 is going to give me 0.037 is equal to I over 2. And then I just need to multiply by 2. So that's going to give me 0.74. Okay, so then the annual rate of interest would be 7.4%. There, did a little bit neater that time. Okay, and last question. So we've got Andrea's borrowing $7,500, so that's going to be her principal. She bought a new car. Her parents charge her interest at 4% per annum, okay, compounded quarterly. So that means interest is going to be 0.04 divided by 4. And then when she pays off her loan, she has to pay that much interest. Okay, so once again, that's going to be the A minus P right there. So then we would add 7,500 plus 785. And then her N, we know, is going to be multiplied by the 4. So however many years it was, will be multiplied. Okay, so we set this up. A is equal to P like that. So my A is going to be that number added together. So let's do 7,500 plus 785 is 8285. Okay, principal is 7,500. And then 1 plus 0.04, so 4% compounded, compounded 4 times in the years. And then we're just going to have a 4n there. Okay. So just like before, we're going to divide both sides by the 7,500. Okay, so then I'm just going to leave it as a fraction here. Okay, and then that's going to be 1.02 to the power of 4n. Okay, now I'm going to, I'm going to take the log of both sides. Log, okay. So then I'm going to have log of 8285, 7,500 equal to, and so now I can use my power. So I've got 4n log of 1.02. Okay. And then from here, okay, in order to get my n, I just need to divide. So I've got n is equal to, and then I'm going to divide by that 4, and I'm going to divide by the log 1.02, and then up top is my log of 8285 divided by 7,500. Okay, and then that's what I need to plug into my calculator, which I should be able to do in one go as long as I use my brackets. So that's just going to be 10, and then I've got 8285 divided by 7500. Okay, and then I'm going to put the bracket on it divided by bracket 4 times log of 1.02. Okay, that should be good. And then I get 1.25, so let me write that down. 1.25, oh, that doesn't make sense though, because that would be 1 year and a quarter. What if I don't do the 4 divided by 4? I feel like that should have worked though. What was the length of the loan? So the length of the loan was 1 year and a quarter. Oopsies, let's spell that right. A quarter of a year would be 3 months. 1 year, 3 months. Yeah. Okay, cool. You could have also done it by just like, so if I go back to here, oopsies, there we go. So there, if we could just like divide by the 4 at the end, but it should still work, right? Divided by 4, yeah. So there you go, 1 year, 3 months. So you can get going on your assignment now. All right, fun story, I got upstairs and was like, that doesn't seem right. And I realize right here, this is supposed to be a 1. That's a 1. Okay, that's a 1. And so then this ends up being 2.5 years. So 2 years, 6 months. But yeah, that was just the error there. Okay, but it's been about a long day, so please forgive me. Bye.